All right, so we're going to go over some problems over work, some problems over power, and then we'll conclude with some problems over mechanical advantage. So I'm going to do a few problems, and then I'm going to expect you to be able to complete the remaining problems. So we start out here with work. Now, work, if you remember from notes, has the formula W equals force times distance. And that W is our amount of work in joules. Okay, so it is W, F, and D. And we can go ahead, we can read problem number 1. It says the smallest bird is the Cuban bee hummingbird, which has a mass of only 1.7 grams. If this bird did 8.8 times 10 to the negative fourth joules of work by exerting an upward force of 3.4 times 10 to the negative fourth newtons, we want to know how far it flied. Well, we start out here and we need to identify our three variables. What's nice about this problem here is that it gives us the work. And it says the work is 8.8 times 10 to the negative fourth joules. Now, the force is given in newtons, and it's at 3.4 times 10 to the negative fourth newtons. We want to know how far it flies or what its distance is. Okay, so that's our question mark. So we plug this back into our equation here, and so we have 8.8 times 10 to the negative fourth joules equal to 3.4 times 10 to the negative fourth newtons, all multiplied by our D for distance. Now, to find D for distance, or to get it by itself, we need to divide each side by 3.4 times 10 to the negative fourth. And when we do this, because we have scientific notation, we must use a set of parentheses. So when you plug these numbers or values into your calculator, wherever you see scientific notation, you need to have a set of parentheses. So we're going to do this. We're going to have 8.8 times 10 to the negative fourth power. And we're going to divide that by 3.4 times 10 to the negative fourth power. We press enter, and we get a value of 2.58. We're going to round this to 1 decimal. So rounding this to 1 decimal gives us a distance of 2.6, and the unit for our distance in our work problems would be 2.6 meters. Okay, so that's how you'd solve a problem for distance. Next problem that we're going to do is right below here on problem number 2, and it says one of the most powerful forklifts ever built was in Sweden in 1991. The lift is capable of lifting a 9.0 times 10 to the fourth kilogram mass a distance of 2 meters above the ground. If the work done by the forklift on the mass is 1.8 times 10 to the 6 joules, what is the force that the forklift exerts on the mass? So again, we're still dealing with work. All of these problems on this particular page deal with work, and so we go through this. We need to list out our variables. So our work is in joules, and so the unit for joules that we find is 1.8 times 10 to the 6 joules. Now, our force is done in newtons. If you see here, there is no force in newtons for this particular problem, and the question also asks, what is the force? Now, the distance that this forklift lifted the object up was 2.0 meters. So we plug these values back into our equation, and so we get 1.8 times 10 to the 6 joules equal to our F for force, we don't know it, times 2.0 meters. Now to get F4 force by itself, we need to divide each side by 2.0 meters. So in our calculators, again, we have scientific notation. So wherever you see scientific notation, you have to take and put a set of parentheses. Now we have 1.8 times 10 to the 6th power, and we're going to divide that. We're going to divide that by 2. So we get a value of 900, Yep, that's right, 900,000 newtons. So there's a force of 900,000 newtons exerted on this particular object. All right, so we've solved for force, we've solved for distance. Now on problem number 3, we're going to solve for work. All right, so we'll read this problem. Suppose an adult blue whale is stranded on a beach. The whale, which lies parallel to the shore, is 15 meters from the water, deep enough for it to swim away in. A group of people line up along the side of the whale to push it back into the ocean. If the whale's weight is 1.5 times 10 to the 6 newtons, and the force of friction that must be overcome by the people is 0.25 times the whale's weight, how much work must the people do on the whale in order to return it to the ocean? Okay, we have a lot going on. You can see it's almost a paragraph just to read through that particular problem. But we're going to have the work, the force, and the D for distance. Well, ultimately here it says how much work must the people do here. So this has to be a big question mark. And then our force. What we're going to have to do here is we're going to have to be able to manipulate our numbers here. We said, hey, the force of friction that must be overcome by the people is 0.25 times the whale's weight. Well, what we need to do is we need to multiply the whale's weight in newtons. So 1.5 times 10 to the 6 newtons. And we need to multiply it by that force of friction, which is 0.25. So what we're going to do here is we're going to put in 0.25. Okay? And so when we do this, again, we have a set of parentheses. So we put that set of parentheses, 1.5 times 10 to the 6th power, 10 to the 6th power. We multiply that by 0.25 because that is the force of friction. And we get a value of 375,000 newtons. So 375,000 newtons. Okay? And then the distance that they must push that whale back into the ocean is 15 meters. So we have our values here to solve for work. So our work is going to be 375,000 newtons times a distance of 15 meters. So we take and we put in our calculators 375,000 times 15. And we get a value of 5,625,000. So the work here is 5,625,000. And the work, remember, the work is expressed in J for joules. A Newton meter is equivalent to 1 joule. All right, so I've solved for work, force, and distance. On 4 and 5, I want you to work through these problems. Again, you may have to read through that, read into these problems, but I'd like you to complete 4 and 5 on your own. The next thing that we're going to do, we're going to talk about power. All right, so power was another formula that we went over. And if you remember this, the power is equal to the W work over T for time. Now, it's very important to remember that the unit for power is watts. Okay, so it has a symbol of W, a capitalized W. Remember that as we go forward. All right, so we have this here. We have a ship, a boat, that has a diesel engine with a power output of 13 megawatts. That is equivalent to 13.0 times 10 to the 6 watts. We want to know how much work is done by this engine in 15 minutes. Okay, so again, we just list out our variables like we did on our other problems. Now, the power is always going to be expressed in watts. We are given capital W watts to be 13.0 times 10 to the 6 watts. Now, the work is something we have to find. Looky here. It says how much work is done over this period of time. And then the time given is 15 minutes. Okay? However, if we want to express the work in joules, we can't have minutes. We have to convert this to seconds. So the way we convert this to seconds, remember 1 minute has 60 seconds. Okay? So what we do here, we multiply 15.0 times 60 and we get a value of 900. So this is 900 seconds. And that's the time we need to use if we're going to solve for W and our work. So the power, we said there is 13.0 times 10 to the 6 watts equal to our W for work, we don't know, divided by 900 seconds. So remember, we must cross multiply. And we have scientific notation. So we got to use our parentheses, okay? So what we do here is we set up a portion of parentheses. So 13 times 10 to the 6 watts. And then we cross multiply. So we multiply that by 900. We press enter and we get a value of 1.17 times 10 to the 10th. So our W here becomes 1.17 times 10 to the 10th, and the unit we express our work is in joules. All right, so we're going to do number 7 because it solves for a different variable here of our power formula. But it says borax was mined in Death Valley, California during the 19th century. It was transported from the valley by massive wagon, each pulled by a team of 21 mules. Suppose each mule's power output was 746 watts. If in a certain time interval, the total work done by the team on the wagon was 2.35 times 10 to the 7th joules, how long did it take for this team to travel that distance? Okay. All right, so we got a little bit of a work to do here. Again, a little bit wordy of a problem, but our power output was 746 watts per 1 mule. We had 21 mules in this team, so we need to multiply that power output by, never mind. Our power output needs to be multiplied by 21. Again, each mule had 746 watts of energy as the power output, but we need to multiply that by 21 because that's how many mules we had in our formation here. So we take 746 times 21, and we get a value of 15,666. So 15,666, it's still watts. And then our work, the work that is done, remember that's expressed in joules. So this is a value of 2.35 times 10 to the 7th joules. And then the time. Ultimately, the time is what we're trying to solve for. So we plug these values back into our equation. So we get 15,666 W4 watts. And then we have 2.35 times 10 to the 7th joules on top. And we divide it by our T for time. Now again, we cross multiply here. So we're left with, I'm going to rewrite this, we're left with 15,666 W4 watts times, I'm going to emphasize the T here, big T, equals 2.35 times 10 to the 7th joules. All right? We got to get big T by itself. So what we do here, we divide everything by 15,666 watts. And on this side, we divide by 15,666 watts. Okay? Now, again, scientific notation, so we have to put this in a set of parentheses. So we get 2.35 times 10 to the 7th. We divide that by 15,666 and we press enter. So our time, we're gonna do some rounding here. Our time is 1,500 seconds. Okay? So that time is 1,500 seconds. All right, so I'm going to skip over some. That's because we've solved for our work and we solved for our time using our power formula. I'm going to skip down to number 10 here. And it says, a team of horses is hitched to a cart. The whole entire team, pulls with a force of 471 newtons. The cart travels 2.3 kilometers in 20 minutes. We want to calculate the power delivered by the horses. So I'm gonna leave some room here between each of my variables, and you'll see why here in just a second. Okay, so ultimately it says, hey, what is the power? We want to know the P for power, the watts that the mules produce. And then we get to this concept of work. Remember, work is in joules. But if you look closely, our value is not given in joules. Well, let's think back just to the problem that we've done. The work is force times our distance. Well, we have our force in newtons to be 471 newtons times our total distance. Now, our distance here is given in 2.3 kilometers. I will help you out a little bit. 2.3 kilometers is equal to 2,300 or 2,300 meters. That unit for distance needs to be in meters. So we multiply that by 2,300. Okay? So we get in our calculators 471 times 2,300. Press enter. We get a very large number, 1,083,300. So I'm going to write this below, just below, 1,083,300 is our value for our work in joules. Okay? Now, our time, the time that it says that all of this took to happen was 20 minutes. Now remember, we need our time in seconds. So what we do here is we multiply our number of minutes by seconds. So we're going to take 20 and multiply it by 60. We get a value of 1,200 seconds. And I'm just going to put 1,200 S for seconds. Okay, so now we have all our values needed to find our power. So our power here is going to be our work in joules. So 1,083,300 joules, all divided by 1,200 seconds. Okay, now I'm just going to plug that into my calculator, and we will see our power output in watts for our problem here. So 1,083,300 divided by 1,200 seconds gets us a value. I'm going to do some rounding here. I'm going to round to the nearest whole number. So the nearest whole number rounds to 903, and that's 903 watts. All right. So I want you on your own to do problems 8 and 9 dealing with power. All right. So now we have one more problem or set of problems to deal with. All right. This is mechanical advantage. And I'm going to do problems 11 and 12 and then expect you to do 13, 14, and 15. So mechanical advantage. We have to be careful here what type of mechanical advantage we're dealing with. If it talks about force, okay, our mechanical advantage, MA, is going to be equal to our output force, all divided by our input force. But on the flip side, if our mechanical advantage is dealing with distance, all right, so it gives that value of a ramp, this is going to put the input distance. And I'm running out of room here, but I'll abbreviate. That's dist for distance, all divided by the output distance. Okay. So problem number 11 reads as follows. It has been proposed that the stones of the pyramid in Egypt were raised using ramps. Suppose one of these ramps had a mechanical advantage of 3.86. If an input force is 6,350 newtons, what would be the output force of that stone? So again, I emphasize force for a reason. We are going to have to use the mechanical advantage of the output force divided by the input force. Again, that is key, is reading exactly what you have. Okay? So our mechanical advantage, it is given. Remember, it is a unitless number, but it is 3.86. Our output force, we don't know because the problem says, hey, what is our output force? And then our input force, the humans moving that stone put an input force of 6,350 newtons into that particular stone. All we need to do, we need to plug this back into our equation. So we have 3.86 equals our output force, all divided by the input force, which we know to be 6,350. So we cross multiply. What we're going to do in our calculators is we're going to take 3.86 and we're going to multiply it by 6,350. So 3.86, we multiply that by 6,350. And our output force is 24,511. All right. So the output force, I'm just going to put output force is 24,511 newtons. That's a pretty impressive ramp if you only put 6,350 newtons in, and you get a output force of 24,511. All right, so now a wedge with a mechanical advantage of 0.78 is used to raise a house. Well, excuse me. I want to skip number 12. I thought it dealt with our distance, and instead, let's go down to number 13, okay? Number 13 deals with distance. So I'm going to have you do number 12 on your own. All right, so number 13 says, a penny farthing is a style of a bicycle with a very large front wheel and a small rear wheel. The cyclist who sits high above the behind the front wheel pedals this wheel directly. The distance the pedals are turned, aka the input distance, in one rotation is about 0.64 meters. If the mechanical advantage of the penny farthing bike is 0.16, how far does the large wheel turn in one rotation? Okay, so we're dealing with mechanical advantage, but we're dealing with it in our distance, all right? So I'm going to put mechanical advantage. I'm going to give some space here. I'm going to put input distance. And then I'm going to put output distance. Okay, so mechanical advantage, again, is a unitless number. We get the value of 0.16. And then the input distance here is this. The input distance here, it says, is 0.64. So 0.64 meters. The output distance is what we need to find out. So our mechanical advantage becomes 0.16 equals our input distance. Distance, 0.64 meters. Divided by our output. We don't know our output distance. Now, I'm going to multiply. I'm going to cross multiply. So 0.16 times our output. So we get 0.16 times the output distance is equal to 0.64 meters. Now we got to get output distance by itself, so we divide each side. We divide each side by 0.16, so 0.16. And we plug this into our calculator. So we get 0.64 divided by 0.16. We press enter. Our output distance, running out of room here, but our output distance is that of 4 meters. So output distance equals 4 meters. Okay? Now, I want you to do problems 12, 14, and 15 on this page. This is all the problems here for our first two sections of chapter 13. Again, you need to do problems 4, you need to do problems 5, 8, 9, 12, 14, and 15. Those are what you need to complete.